Topic I want to talk about today is the concept of center of mass. Center of mass is a concept that you should have a pretty good feel for. It's the center of mass or the center of gravity. They're basically the same thing. Abbreviated COM or COG, center of mass, center of gravity. And that's where something balances. It is also the center of gravity if the gravitational force is constant across the system. So that's why I say center of mass is equal to center of gravity, because the gravitational acceleration is constant everywhere. So the gravitational force doesn't vary with space. It might vary with the mass, but it doesn't vary in space. If you want to ask what's the center of mass, the Earth-Sun system versus the center of gravity, now it's different because the gravitational force varies out in space, right? But the gravitational force doesn't vary on Earth. So on Earth, the center of mass is the same as center of gravity, unless we're taking into account tiny little changes in the gravitational force. Right? So if you take an object, it doesn't matter what it is, and you balance it, and let's say we could take this object and this is actually the state of Massachusetts, in case you didn't get that. And we want to find the center of mass. And we were to take this and cut it out of a piece of cardboard or something. It might balance, let's say, it might balance somewhere like there, right? That you got somewhat of the same, to some extent, the same amount of material on any side of that point. So we need to figure out mathematically where the center of mass of something is. And careful also, because when we're talking about the center of something, we may talk about the geographic center. I guess the geographic center would be the geometric center, is sort of equidistant as much as you can from all points. Whereas the center of mass, there's mountains. Oops, this didn't let me draw. There's mountains in western Massachusetts, so there may be more land mass out there. So maybe the center of mass is actually further towards the west because there's more land mass out there. I don't know that that's true, but so the center of mass may be different than the sort of geographic center. The center of population, there are many more people in the Boston area, and sort of in the Boston suburbs, and so the center of population is going to be more to the east than the geometric center or the center of mass, center of population. So in any case, so there are different kinds of centers that you can talk about. We're going to talk about the center of mass, and the center of mass is literally where something would balance due to the distribution of mass being balanced about a point. So rather than talking about something complicated like the state of Massachusetts, let's just talk about point masses. Let's start with point masses. Let's say that we have 2 point masses, in other words, masses that don't take up any space, and they each have a mass of 1 kilogram. They're separated by 1 meter. Where is the center of mass of these 2 point masses? Now, you might say, well, there's no way to balance 2 point masses because they're not attached to each other. But we're talking about this imaginary center of mass. If they were connected by a massless rod, right? If they were connected by a massless rod, where would that rod balance? And I think you could guess that the rod is going to balance right in the geographic center, right, at 50 centimeters from either side. 50 centimeters from the mass on either side, halfway along. Let's say I then added a third mass, and let's put that third mass a little to the left, on the right. Let's just put the third mass here. It's a point mass. Again, let's not worry about the fact that it takes up any space. And I don't really care about how much mass it is. Just ask what happens to the center of mass. Well, in that case, now there's more mass on the right than the left, so the center of mass is going to shift towards the right. It's not necessarily going to move all the way to the first mass, but the center of mass, which was here, is going to shift over somewhat. It depends on how much mass and where the mass is placed, but the center of mass will shift over to the right a little bit. So we need to calculate what the actual mathematical center of mass is. So we need a formula. So let me write something down. So the center of mass in one dimension, if we're just putting point masses, right, masses that they themselves don't take up any space, along a line, right, that imaginary massless rod, and where would that imaginary massless rod balance? It's going to balance at the point that is given by x sub cm, center of mass. I left off the O, x sub center of mass. It's the position of the first mass times the mass of the first mass, plus the position of the second mass times the mass of the second mass, plus the position of the third mass times the mass of the third mass, plus ... if we have additional masses, divided by the sum of all the masses. Sum of all the masses is just the total mass available. So this is also more simply written as the sum sign, right? That's the Greek letter epsilon, it's capital epsilon, of xi mi, where we're summing over I, divided by mass total. So let's just do the example that we did above. But in order to give our masses positions, what do we have to do? Because what is the position of the 2 kilogram masses that I wrote down? They're a meter away from each other, but that's not their position, right? We have to put them on a coordinate axis. So we got to define our coordinate axis. And it absolutely doesn't matter where your coordinate axis is, but we're just going to define a coordinate axis. And let's just put our coordinate axis so that the origin is at the first mass and 1 meter is at the second mass. So that means that x1, the one on the left, is equal to 0, x2 is equal to 1 meter, right? So that's the 2 masses above. We'll leave off the third mass for now. And m1 is 1 kilogram, and m2 is 1 kilogram. So we'll go ahead and plug that into the formula, the sum of xi mi. So x1 is 0, m1 is 1 kilogram, plus the sum of the position of the second mass, which is 1 meter, and the mass of the second mass, which is 1 kilogram, divided by the total mass, which is 2 kilograms. I wrote something wrong. Hold on. Go ahead and plug those numbers into your calculator. You don't really have to do that because 0 times 1 is 0. 1 times 1 is on top. On top, you've got 1 meter kilogram divided by 2 kilograms is 1/2 of a meter, or 0.5 meters. The center of mass is 0.5 meters, 50 centimeters. It's halfway between the two. What if we now add the third mass? So all 3 masses are 1 kilogram, so m1 equals m2 equals m3 equals 1 kilogram. I'll use the same coordinate axis. Again, it doesn't matter where your coordinate axis is. This is always going to work. And in this case, x1 is 0, x2 is 1 meter, just like before, and I'll add x3 at 0.8 meters. It still has a mass of 1 kilogram, so that we can say that the center of mass of this system, go ahead and just plug that into m1x1 plus m2x2 plus m3x3 over m1 plus m2 plus m3. Plug it into the formula from the page before. I'll just highlight it here, right? We're plugging it into that formula. And plug it into your calculator, you get 0.6 meters. So the center of mass has moved over from 0.5, center of mass has moved over from 0.5 meters to 0.6 meters when I added that third mass. So just pointing out that it doesn't matter where your coordinate axis is, but you have to pay attention to your coordinate axis. If I take the same 2 masses separated by 1 meter and I put my coordinate axis so that it's at the center, so that 0 is at the center, then the position of the mass on the left is at minus 0.5 meters. The position of the mass on the right is at plus 0.5 meters. Plug them into our sum of m1 x1 plus m2 x2 over m1 plus m2, and think about it, plug it in, you get 0. Does that make sense? It's a different answer than last time. Last time it was 0.5. Well, yes, because it's a different axis. 0 is at the center between the two. So it's just relative to wherever you choose your 0. So we can just do this in the same thing in 2 dimensions, since things do exist in 2 dimensions. So just like always, when we move into multiple dimensions, we break it up into the x and y direction. We treat them completely independently. So we've got the exact same equation. Y center of mass is the sum of m I y I over m total. X center of mass is what it was before. So we can find this, and notice that I did switch the positions of m1 x1 or x1 m1. It doesn't matter, obviously. Multiplication is commutative or associative or whatever that property is. Anyway, so in the y direction or in the z direction, we've got the exact same equation. So we can find the center of mass of things in multiple dimensions, except that the way I wrote this here, there are 3 objects, so I forgot to put the third one, m3x3 over m3 plus m3y3 plus m3. So there are 3 objects. So I just now have to choose a coordinate system that's in 2 dimensions for this problem. So I'm going to choose the coordinate system that has its origin at object 1, and the plus x direction goes to the right, plus y direction goes up, and I'm going to start to fill in these numbers, right? M1 is, let's just make them all 1 kilogram masses. M is 1 kilogram, all of them, M1, M2, and M3. So 1 kilogram times the position of M1 is at x equals 0, plus 1 kilogram. Oh my gosh, I can't write. 1 kilogram times the position of object 2, it's at 1 meter, plus 1 kilogram, and the position of object 3, notice that's at x equals 0 again, so that the center of mass, that's the top of that fraction, so that the center of mass is going to be, on top we've got 1, and on the bottom we've got 3, is going to be 1/3. 1/3 of a meter, or 0.3 meters. In the y direction, we're going to get 1 kilogram times the position in the y direction of object 1, which is 0, plus the position 1 kilogram. Object 2 is 1 kilogram. Its position in the y direction is 0. Object 3, 1 kilogram. Here, I forgot to put the 3 kilograms on the bottom here. 1 kilogram times, so the object 3 is at minus 1 meter, and M1 plus M2 plus M3 is 3 kilograms. So the center of mass in the y direction is negative 0.3 meters. So the center of mass of this system, where is that center of mass? Picture that center of mass. Where does this thing balance? It's about 1/3 of the way along and 1/3 of the way down. And so that center of mass is, is right about there, center of mass of the system. That's where it would balance. About 1/3 of the way along and 1/3 of the way down. Okay, so that's center of mass for point masses, and we can do that in 3 dimensions. I know we rarely deal with the z direction, but we do sometimes, and so we can just write this shorthand as a position vector, r. That's a position vector, right? So in 3 dimensions, x, y, z, r is a position vector that just points out into space, and r has an x component, r has a y component, and r has a z component. And so that's just what this shows, is that it has an x component, a y component, a z component, and if r is the center of mass vector, then those 3 components are each of the individual center of mass. It's just shorthand showing the equations, these 2 equations, and then with the z center of mass also. So what about the center of mass of a continuous object, of an object that takes up space? The center of mass of, let's say, a meter stick, right? So clearly, I think pretty clearly, the center of mass of a meter stick is its center, right? And that is, this does assume that the meter stick is made up of constant density material, right? The density doesn't change. It doesn't get more massive per unit length as we move along the material. And so the center of mass of that meter stick, where would that meter stick balance? It's going to balance at the center at about 50 centimeters. We can get a little bit more complicated than a meter stick, and we could ask, what's the center of mass of let's say, an object which is sort of triangular. And so now, per unit distance, right, as we move along the thing, there is less and less mass per unit distance, right? So in a sense, its density for a given distance is smaller, right? Well, we should probably talk about what is density. Density, I think density is mass per unit volume. Or we can talk about, and that's the Greek letter rho, or we can talk about areal density, which is mass per unit area, we can talk about linear density, which is mass per unit length. So I think I'll stick with the Greek letter rho for density, and just we need to know which density we're talking about when we're talking about things. And typically, like for the meter stick, we won't worry about the fact that it takes up volume. We'll just think of it as a one-dimensional object, so it's really got a mass per unit length, right? So anyway, so let's just see how we deal with the center of mass of a continuous object. What is the center of mass of this red triangular thing, right? Oh, and by the way, this little thing, the triangle that I put beneath the meter stick, that thing, that is the fulcrum. That's where it would balance if we would actually put a fulcrum under there. That's the thing that it balances on. So where would the triangle balance? It wouldn't balance right in its center because there's more mass to the left than there is to the right. So it's going to balance somewhere over here, right? It's going to balance somewhere over there. So we can figure out where would it balance if we could balance it if it's a continuous object. So let's just think about that, how we could calculate that. So what we can do with let's just start with the meter stick, the easy one. We can just say, oh, well, actually a meter stick is made up of a bunch of point masses. Now, a point mass is something that takes up no space, but we can approximate it, and we could break up the meter stick into, let's say, 100 1 centimeter long pieces, right? We could say 1 centimeter long pieces, and we could take the whole mass of the meter stick, and we could say that each of the, let's say that the whole mass of the meter stick, mass total, was, I don't know, let's just say it's 100 grams. So therefore, each piece, therefore M1, each piece, or M sub I, is going to be, if we break it up into 1 centimeter pieces, 100 pieces, then each one weighs, 1 gram. Okay, 1 gram. And the position of each piece, X1, we could say is that we could start our origin at the left-hand side and say x1 is 0, x2 is at 1 centimeter, x3 is at 2 centimeters, ... right? And so we could then do a sum of 100 pieces, and this wouldn't be too hard to do, over the M total and figure out what the center of mass is. So, therefore, X center of mass is... So if you actually did that sum, and by the way, notice that I'm starting the first piece at 0 centimeters, so there's going to be 0 through 99, right? We're going to take the first piece and its mass times this position, plus the second piece is mass times this position, the third piece, the fourth piece, the fifth piece, up to 99, because the first piece is point number 0, and the last one is therefore number 99. There's 100 pieces. And we're going to sum up. So look here, we're going to sum up the mass of each piece times the position of each piece. These pieces' position is just its piece number, right? Because the 0th piece is at 0 centimeters, the first piece is at 1 centimeter, the second piece is at 2 centimeters. And we're going to divide it by the total mass. And you can actually do that math. It's not that hard to do the sum on the top. You get 5,000 gram centimeters. And on the bottom, you get 100 grams. And so the center of mass is, it's 50 centimeters. That's the center of mass. Okay. So we found the center of mass of a meter stick. Well, there's a better way to do that because each piece is not actually a point mass. We really want to make it smaller. So let's break the meter stick into 1,000 pieces instead and do a sum over 1,000. Well, actually, let's just break them up into infinitesimally small pieces. So instead of it being a sum of MIXI over M total, we're going to break them up into infinitely small pieces. Let's just pretend. And we're going to call each piece a width dx. So each piece, we're just going to take really, really, really small pieces. They still have position x sub I. And there's just more and more of them as we make them smaller and smaller. The width of each piece is dx, whereas before the width of each piece was 1 centimeters. We still have a position, which is going to be anywhere from 0 to 100 centimeters. And so now we want to know what is the mass of each of these little pieces, right? We're breaking it up into a piece of really small width, and what's the mass of each of those pieces? That's what's going to go here. X still, we're going to add up all the pieces from positions of 0 centimeters all the way up to the position of 100 centimeters. So we're going to add this up from 0 to 100 centimeters. But what is the mass of each piece of width dx? Well, this is where density comes in. Remember, the linear density, if this is just a one-dimensional object, is mass per unit length. So, therefore, the mass of each piece is going to be the density of the meter stick times the length of any particular piece. So therefore, the mass m sub I of each piece is the density of the meter stick, the total mass. I'm sorry, let me make this a little clearer. Notice that, so now the mass of each individual piece is the density of the meter stick times just its width, dx. So therefore, let's make sure you see that, right? Density is total mass over total length, or if it's the same density throughout, then it's any mass over any length, and so the mass of an individual piece is density times length. The length of each piece is dx, so the mass of each piece is rho dx, where rho is the density of the meter stick. So therefore, x center mass is equal to the sum of the mass of each piece, which is rho dx, times the position of each piece, which is x, over the total mass. Rho is a constant, right? That's the density of the meter stick. And the density of the meter stick, we're assuming the density of the meter stick is just the total mass of the meter stick divided by the total length of the meter stick, which is 1 meter, right? The total length. And we're assuming the density is constant throughout, so that we can take the density out of this sum, and we've got a sum of, I'm just going to change positions of those two variables, of x dx over m total. So therefore, the center of mass of the meter stick is what's called an infinite sum, because remember, we made these dx's infinitesimally small, so we had an infinite number of them. They still go from 0 to 100 to 1 meter. But this is an infinite sum, which is called an integral. So we've got rho over mass total times the integral of x dx. And we're going to add that up from a position, because x is a position, from 0 to 100 centimeters. We'll do it in centimeters. Remember, the mass of the density of the meter stick was just mass of the meter stick m total over the total length of the meter stick. We have m total on the bottom, integral of x dx from 0 to 100 centimeters. So the m totals cancel, so that we just have 1 over L out front. We've got x to the first power, dx. So let's go ahead and write this integral. So there's the integral copied from the other page. This is for the center of mass of the meter stick. I'm going to evaluate it, which I've started writing on the second line, but I didn't finish. 1 over L. I'm going to evaluate the integral x dx, x to the first, right? There's a implied 1 here. X to the 1 more power, that's 2. Over the 1 more power, that's 2. Evaluated from 0 to 100 centimeters. And so what that means is that we're going to say 1 over L. We're going to plug in 100 centimeters over 2 minus 0 centimeters squared over 2. So we just evaluate it at the two limits and subtract. And what is L, right? L is the length of the meter stick. That is also 100 centimeters. So what we end up getting is, oh boy, no surprise there. If you do the math, we end up getting 50 centimeters. The center of mass of the meter stick is at 50 centimeters. But that's an example of how to do a continuous distribution of mass. But here's the punchline. Even though you may have a hard time repeating that for a different kind of distribution, here's the punchline, right? The center of mass for a continuous distribution, instead of a finite sum, is an infinite sum. It's the integral of x dm over m total. It's the position x of each of the little pieces, which each of the little pieces have a mass dm, right? In that case, the mass dm was the density times dx. That was a special case for constant density, but it's just a position of each piece times the mass of each piece. The position of each piece times the mass of each piece added up for all of the pieces divided by the mass total. So again, the center of mass is the integral of x dm over m total, where dm is the mass of each little piece at position x. So this is the same as the finite sum, just written for infinitesimally small pieces added up. Next time we're going to talk about how all forces act through the center of mass of an object. That's why we care about the center of mass of an object in this class in particular, because all objects act. This is important. This is like the most important thing. All objects that are extended, that take up space, act as if all of their mass is at their center of mass. They act like they're point masses, and that's how come up until now we've been able to treat everything like a point mass. We haven't really had to deal with the fact that things take up space.